Hello, and welcome to today's lesson. It's a bit long, but there's a lot of things in it, and I hope you get a lot out of it. So let's begin. Just to review, the idea of finding probabilities with the normal distribution is to basically find areas underneath a curve between two boundary points. So what we're going to do is use what's called the Normalcdf function. This stands for the Normal Cumulative Distribution function. It can be found on our calculator under the VARs menu button. You see it right there, distribution. So hit second VARs to access it, and here's the menu. We'll be using the Normalcdf, and then a little bit later on, the inverse norm. Things to keep in mind, it can calculate the area of the shaded region underneath the curve between some left point and right point. Sometimes these are also called the lower bounds and upper bounds. This is a schematic of how it'll work. We'll have some boundary points we're trying to find the area of, some A value and B value, and then the curve will be centered at some mu coming from the problem in the context, and then we'll also have the standard deviation for the curve as well. So using those 4 bits of information, we plug it into the Normalcdf function, and it'll give us this shaded area, which is going to be the probability. Here we have a left-tailed calculation where we need to go all the way out to negative infinity. Now we can't enter that into the calculator, so we use an approximation, negative 1e99, or just a lot of 9s, negative 99999. This will apply to situations where we see the words less than or at most. Alternatively, when we do a right-sided or right-tailed test or calculation, we'll have some lower bound, and we're going to go all the way up and out to positive infinity, and the same concept again. We can't enter infinity into the calculator, so we use very large positive values to approximate with. So we can use the lower bound A, 1e99, and then again, of course, the mu and the standard deviation describing the shape and location of our curve. Or you can just spam a bunch of 9s as well for the upper bound. And again, this will be used for whenever we use problems that have greater than or less than in the context. Also later on, we'll reverse this concept. So this time we have a certain area in mind that we need to calculate, or probability we're trying to figure out. This applies to percentiles. And we'll need to know the x value that demarks that location on the curve. So that way there's a certain amount of probability or area to the left of it, or possibly to the right. Whenever we want to find the x location that separates the areas of the curve, we're going to use the inverse norm. It's kind of inversing the idea of the Normalcdf function. So in this case, we'll need to tell it the area we need to the left of it, and then again the shape of the curve. Where is it located, mu, where is it centered, and then how distributed is it by our standard deviation. So here we have an example. We have 20 to the left and 80 to the right using the complement rule. And this calculation will tell us what value of x breaks the whole normal distribution up into those two proportions. Let's try some problems here, and this is going to be our context. So we have some information. The number of chocolate chips in an 18-ounce bag of Chips Ahoy cookies is approximately normally distributed. So once we see those words, we can draw our normal curve. Some other information, we're told the bags have a mean number of chocolate chips of 1,262, and then the standard deviation amongst the bags is 118 chips. So once we see that normally distributed, we draw our normal curve, and then we'll start to fill in some values, these standard deviation markers, to give us some help when we start to solve some problems. Alright, so here we have our curve, and we filled in the values. So it's centered at the mean, so we have 1262 right here in the middle, and then every standard deviation is separated by 118 chips. So 1262 plus 118 lands us at the first standard deviation. Another 118 chips puts us at the second, the third, and then we subtract to go to the left. So that gives us an idea of what our curve looks like as we go through these next couple of problems. Alright, so I kind of color-coded these to give us an idea. So sometimes you might want to find out some set number of chips. So what's the probability that if we pick the random bag from this collection, that it would have between 1,000 and 1,400 chips, or fewer than 1,000 chips? That's one of those out to infinity style things. Or maybe what's the percentile rank for a certain number of chips in a bag? This bag has 1,475 chips. It has more chips than what percent of all the other bags in the population. So for all these, we're trying to calculate an area or a probability, and we have certain values for x. So whenever we have x values or bounds, we use the Normalcdf, and it gives us the area which corresponds to our percentage. or probability. Now, in the other case, here we have some in orange. These are giving us an area to work with, and we're trying to find the X value that demarks that area or that probability. So how many chips are in a bag needed to be in the 30th percentile? So this is going to be, some chips are going to be bigger than 30% of all the rest. So where is that X location? What is that number of chips? Determine the number of chips that make up the middle 90% of bags. So again, we have a percentage that we're given, and we're trying to find locations on the X value, which represents numbers of chips in this context. Let's try some applications. What is the chance that a randomly selected bag contains between 1,000 and 1,400 chocolate chips? So we know it's normally distributed, so we have our curve. We have some places marked to give us an idea. So the first thing we would like to do is shade in the area so we can see what we're working with. So 1,000 chips would be somewhere down here, 1,400 chips would be somewhere over here, so we go ahead and shade that region in. The normal CDF to calculate what's the area of this shaded region. So we get our normal CDF function, plug in all the information we have, and we see that we get a number here, let's see, 86.56. So the chance that we'll pick a bag with this number of chips in it would be roughly 87% chance. Next problem. What is the chance that the randomly selected bag contains fewer than 1,000 chocolate chips? So we have our normal curve. Here's the 1,000 mark, and fewer would be to the left of it, so we need to shade in this little region down here. And so to calculate that probability, we grab our normal CDF function again, plug in the negative infinity. I'm using the 1E99. Our upper bound is the 1,000 chips, and everything else stays the same. And so we see we get our calculation, and it's very small chance. So it looks like we have a 1.3% chance of getting a bag that would have fewer than 1,000 chocolate chips in it. Next problem, what is the chance that a randomly selected bag contains more than 1,200 chocolate chips? So we have our normal curve. 1,200 would be somewhere in this standard deviation portion right here, and more than to the right is what we want to shade in. So again, normal CDF, our lower bound this time is 1,200, the upper bound is in essence infinity. Everything else stayed the same from the previous couple problems. Running through the calculation, we see that there is a 70% chance that a bag will have more than 1,200 chocolate chips. What is the chance that a randomly selected bag has fewer than 1,125 chocolate chips? So again, where is that on the graph? Somewhere in between these two markers. So that's our shaded region, and it's less than or fewer than, so we want to go to the left. So negative infinity up to 1,125. Hit the enter button. Once we get it to calculate, we see that there's basically a 12% chance that a bag will contain fewer than 1,125 chocolate chips. What is the percentile rank for a randomly selected bag that contains 1,475 chips? So if a bag has this many chocolate chips in it, it has more than what percent of all the other bags out there? All right, so where's 1,475? It's over here on the right side. All right, so this is going to have more chips than what percent of the rest of the population? So we're already all the way to the right, so we should expect something bigger than 50 because we have over half the graph already shaded in. And so we have from negative infinity up to that mark, 1,475. Running a calculation, we see it's going to have a lot more chips than a lot. In fact, it's going to have more than 96% of all the other bags out there. Same problem again. What is the percentile rank for a bag that contains 1,050 chips? All right, so 1,050 is round about here-ish somewhere. And so it's going to be in a low percentile rank because it's below at least 50. It's always in the middle. So we have to calculate, okay, what's that area right there? What percent of all those bags have fewer than 1,050 chips? Negative infinity up to 1,050. Very few. So we see that this would be roughly in the 3.6 percentile rank. It has less chocolate chips, or more chocolate chips than 3.6% of all the other bags out there. All right, now we see the orange color coding. This helps us see that we're going to reverse this concept. Now we're being asked, okay, here's the percentile we want to calculate. How many chips does that correspond to? All right, so 30th percentile, we know it's 50th is in the middle, so it's going to be shaded somewhere on the left, and these are just sketches to give us a concept. So somewhere over here, we need to find out, okay, what number of chips give us 30% less than it? All right, what's the 30th percentile for the chocolate chips? We're trying to find the X value. So we plug that into the inverse norm. We need 30% to the left, the mu, the mean, and our standard deviation is the same. And so it tells us we have we'll round off to the nearest chocolate chip. So it looks like if you want to find the 30th percentile, that's going to be where a bag has 1,200 chips in it. All right, here's probably the trickiest one in the batch. Determine the number of chips that make up the middle 90%. So the middle, everything in between. So that's what we want to talk about with the middle. So there's actually two x values we need to find. So 90%, and one tricky thing about the inverse norm, it only calculates an area to the left of it. So we can't really just tell it to find the middle 90%. We have to do this in pieces. So what's to the left? Well, if the 90% is in the middle, that means there's 10% left over. And not only that, it's symmetric. So that 10% is going to be split to those two sides of the 90%. So on one side, we'll have 5% here. And on the top end of the tail, we'll have another 5% here. So this all adds up to 100. So we have the middle, and then 5% to the lower, and 5% to the upper. All right, so the inverse norm, again, only works for the area to the left. So if we want to find our lower bound that demarks this location, we need to find out, okay, what x value has 5% of it to the left of that mark. Okay. Conversely, on the other side, we need to find out this side, this little marker, where it's the number of chips up here. So here we have 5% plus that middle 90%. So there's actually 95% of the curve to the left of this spot down here. 5% over here, the complement rule, 95% to the left. So we kind of have to do this in two stages. All right, so on the left side, we need how many chips have 5% of the area of the curve to their left? And then over here we have what number of chips has 95% of the area to its left. And so we run the calculations, we get some numbers down here, and we'll kind of round off to the nearest whole chip. So we see the middle 90% of bags contain between 1,067 and 1,456 chocolate chips. All right, that concludes our lesson today, where we went through some examples using the normal CDF and the inverse norm. Try them again, walk through them again, and thanks for watching.